Hi and welcome to an introduction to Physics A-Level at Halmer Green Senior School. The goal of physics is to understand how things work from first principles. This is a key difference between studying GCSE physics and A-Level. You will be asked to explore the history and scientific method that has led to our current knowledge in physics, as well as understanding the underlying science. You've all got different reasons, I'm sure, for choosing Physics A-Level. Firstly, obviously, it satisfies the requirements for hundreds of different degrees and careers in science and engineering. But as a subject, it reveals the mathematical beauty of the universe at scales ranging from the subatomic right up to the cosmological. In addition, studying physics will strengthen your quantitative reasoning and problem-solving skills, and these are valuable in almost any area beyond physics. Physicists are generally interested in the root or ultimate cause of phenomena and usually frame their understanding in mathematical terms. Studying A-Level physics for the next 2 years will start you on a journey of gaining knowledge that you can apply towards solving practical problems, answering big questions and developing new technologies. Some of these are suggested on the next 2 slides. Feel free to pause the video and copy the URLs to follow any that you find interesting. Some of these links are a really good place to start your studies. The course we follow at Halmer Green Senior School is AQA A-Level Physics. There is the possibility of studying it for 1 year and being entered for an AS, but typically we expect our students that take up A-Level Physics to be with us for the 2 years studying the full A-Level. If you want more specific details, you can always log on to the AQA website and follow the links to the A-Level Physics course. In the first year, you will start your studies by having a look at various measurements and how they are made, the equipment we use to make them. We will consider the errors in making those measurements and how that can be calculated and how that affects the results. So our first unit of study is really all about the practical work. You'll be introduced to some of the mathematical elements of the course as well. The rest of the year is split into 4 topics. The first is all about particles and radiation. It's a dive into the quantum world, so the subatomic world. Waves, mechanics and materials, and electricity are the last 3 topics in year 1. In year 2, we start again by looking closer at the practical skills that we have learnt in year 12 and looking at how we can improve and extend them in year 13. We look further at some of the maths, some of the new maths that will come up in year 13. And then again, the rest of the year is divided into topics. The first is more mechanics, so it moves on from the linear motion of year 12 to start looking at periodic motion in year 13. The next topic, thermal physics, includes gas laws, fields and their consequences, and then nuclear physics. Rounds up the year 2, and then at the end of year 2 we choose an option. There are a number of options if you go onto the AQA website. The one that is most commonly chosen and the one we usually teach is the astrophysics option, although we can always discuss this if needed, if appropriate. At the end of year 12, you will sit 2 exams. If you are going on to study the A-Level, these are internally set and assessed and do not count towards your full A-Level. They are important, however, in setting UCAS grades and looking towards the progress that you're making and entry into year 13. The 2 exams are an hour and a half long. Both papers cover the entire Year 1 course, and you are examined in both the theory and the practical skills that you have learnt in Year 12. At the end of Year 13, you will sit your external A-level exams. These consist of 3 exam papers. Paper 1 is largely Year 12 work. Paper 2, Year 13 work. Paper 3, a mixture of Year 1 and Year 2 work, and includes a practical section and the option, which is usually astrophysics. Each exam is 2 hours long. The practical element of the course is examined as part of the normal exams at the end of year. In every paper there are questions geared at assessing your knowledge and understanding of key practicals that you will have completed, as well as trying to assess your competency, so your ability to evaluate or conclude or manipulate data, draw graphs, that type of thing, and it is part of the actual exam. Alongside that, there is a coursework element. It is assessed internally by your teachers. We have been assessed 3 times now by AQA, all assessments came out really well. The way we set up our practicals has been fully endorsed by the exam board, and our pupils, generally speaking, find this one of the more straightforward aspects of the course. There are 12 required practicals that you will complete, and alongside that there will be a number of additional assessed practicals. These assessed practicals will be completed in a lab book, and different elements of the practical that you do will be assessed. You will always know which part of the practical is being assessed. There are 5 competencies that you are assessed against, starting with actually conducting the experiment. Can you safely use the equipment? Can you use it appropriately, properly? Do you select the right kind of equipment? The second competency is about your planning. Can you identify variables? Can you reduce errors? Do you understand what a suitable range would be? That type of thing, as well as controls for your experiment. The third competency is all about safety aspects, and then competency 4 is about your recording and manipulation and use of data, and competency 5 are, well, it's concluding and evaluating skills. These should sound very familiar to you. It does follow on quite nicely from the practical, required practical and practical skills you would have begun to work with at GCSE. On our website, we've already posted some of the transition material that you might like to look at. One of the things that is recommended is the CGP Head Start to A-Level Physics book. There is an online copy, or you can buy it for less than £5 from CGP. Particularly important for anyone that has studied the dual award science rather than the triple single sciences. It just covers the GCSE that you may not have done, having missed that third separate science. The AQA textbook that we use throughout the A-level, again, you would be expected to purchase your own, although anybody that would have difficulty with that can be provided with one. As far as actual lessons are concerned, you will have 5 1-hour lessons in physics every week. The lessons will cover both the theory and practical content. You will be expected to complete the 12 assessed required practicals and any other assessments in order to pass the coursework before the end of the second year. You will be expected to complete up to 5 hours homework / independent study. There'll be a mixture of that each week, but you will be guided in that by your teacher. Typically you will sit a test at the end of every topic. These are sometimes open book tests. They're not always in silent exam conditions, although there are 6 AP points every year, assessment points, and they will be matched with a more formal style assessment at those key points. Key difference between studying physics at A level compared to studying at GCSE is that you really will be expected to start showing that you can work independently, that you can be responsible for your own work, you can manage your own time, and you can develop into an independent thinker. So somebody who is a scientist as opposed to someone studying science. On the next slide is a really simple activity I'd like you to have a go at, just to illustrate the difference between being a scientist and just learning science. So this first activity is a little challenge. It is quite straightforward, and it's aimed at problem solving. The idea is to show you that you can be given some basic tools, basic facts, basic bits of information, or even just some equipment, and that you have to use your observation, reasoning, thinking skills to come up with a solution to that problem. So you're asked, if you can, just get a piece of paper and a penny, draw around the penny and cut out the hole so you have a penny-sized hole. Then get a larger 2-penny piece and, without ripping, tearing or making the hole larger, pass the 2p through the 1p hole. Good luck. Pause the video whilst you give it a go. If you're not having any luck, the solution is on the next slide for you, so you can have a sneaky peek. So the solution, a little bit fiddly, but it is possible. I hope you managed to do it. Well done if you managed to solve it without having a look at the answer. You can see the explanation here for what's happening. Obviously, when you fold the paper in half and pull the two sides up, the hole becomes elliptical in shape, increasing the area of the opening in that plane and enabling the 2p coin to slip through. A simple activity and a simple solution, but it does show you what being a scientist is all about, thinking your way through until you come up with a solution. And then, if you haven't already done so, apply the science to it. Why has that worked? So a slightly different task for you here. This one is based on observation. It's not a problem that you have to solve, but more a theory to develop. Can you explain the observation that you are making? Again, it's quite a simple practical, quite a simple observation, may even be one that you've seen before. The key here really is to develop a scientific, scientifically reasoned theory for the observation. When you think you've got one, just have a little think. As scientists, we normally confirm our theories by trying to prove them wrong. So what other experiments, what other tests could you do that would provide evidence that the theory you've come up with is correct? The observation you can see there is you have 2 cans filled with Coke, and one is floating, one is sinking. So hopefully you realise that if one's floating, one's sinking, there is a difference in buoyancy, and buoyancy is related to density, density being how much mass something has per volume. Both the cans are equally sized, equally filled with liquid, and therefore have the same volume. Which maybe leads us to think that maybe their mass is different. Other ideas might be something to do with the colour of the can. Maybe the different coloured cans make the liquids inside different temperature, and temperature is something else that can affect buoyancy. As things get warmer, particles spread out, they become less dense and float. So maybe there's some sort of temperature difference. Another possible theory that you may have come up with would be something to do with what is in the can. So is it something unique to Coke, or is there, a different brand? Would that behave differently? Or is it something to do with the fact that one's diet, one's not diet? If you look at the images on the screen, some of those hypotheses have been tested. You can clearly see that the colour of the can is not really making any difference. We've got a green can floating, an orange can isn't. Blue can's floating. We've got 2 lots of Pepsi there. One floats, one doesn't. So you can try different scenarios. You might even take it further and do things like actually check the temperature of the liquid in the can. There are all kinds of other measurements you can make. The answer, in fact, just if you weren't sure, is that the NutraSweet, or the, well, it might not be NutraSweet, but the sweetener in Diet Coke is 100 times sweeter per volume than sugar. So there's very, very little sweetener in the can, and most of it is in fact water. Whereas in the regular Coke or Pepsi or full sugar drink, obviously that sweetness is brought about by packing it full of loads and loads of sugar. That sugar increases the density of the liquid inside the can so that it sinks, and the Diet Coke with the no sugar in floats. So this process of making an observation, trying to understand what's happening, trying to think through reasons, ideas for why they might happen, setting up some further experiments, making additional observations to prove or disprove your ideas, until finally you have one theory that seems to fit all of the evidence that's offered. This is the scientific process, and this is something you're going to go through multiple times during the A-level and beyond if you carry on studying in science. Incidentally, quite often the experiments we set up are to see if our theory or prove our theory wrong rather than prove things right. It's kind of like last man standing. If everything has been proven wrong, the theory you're left with must be the correct one. So that brings me to the end of this very brief introduction to physics at Harmer Green Senior School. Obviously, if you wish to know more, then have a look at some of the links that have been included in this PowerPoint. I'm going to leave you on the next couple of slides with a puzzle and then a conundrum. The solution to both are on the end of the video, so if you want to actually have a go at trying the puzzle and the conundrum, you will need to pause the video on the appropriate screen and then press play to find out the solution. Thank you. Goodbye.